Hi, and welcome back to another MTH112 lecture. The final topic for this term is hyperbolas. And hyperbolas are also our final sort of the final type of conic section that we're going to discuss. Now, a hyperbola, like an ellipse, is based on the distance of a point from two focus points. The difference is that instead of looking at the sum of the distance, we're going to look at the difference between the distances. So if we look at x1, y1, if this is d1, 1, and this is d1, 2. So this is the distance of point 1 from focus 1, and this is the distance of point 1 from focus 2. Okay. What we're saying is we're going to define some distance d that is equal to d1, 1 minus d1, 2. And so whether we're talking about a point on this half of the hyperbola or a point on this half of the hyperbola, so like inverse functions, hyperbolas are always going to have two branches. But regardless, if we take the difference between these two distances, we're going to get this distance d. So this should actually probably be an absolute value. Okay, because it depends on which one we define as 1 and 2. All right, so let's take a look at these things. We need to have a few more pieces of vocabulary here. They're a bit more complicated, but they're not anything we can't handle. We have our familiar focus points. We have vertices. Now this time, remember with an ellipse, the vertices were further out from the center than the focus points. With a hyperbola, the vertices are between the focus points and the center. Okay. The axis that goes through those vertices and therefore through the focus points is called the transverse axis. There is another axis we talk about that is perpendicular to that axis, also through the center, and we call that the conjugate axis. Now, we're going to, so this rectangle, this dotted rectangle you see here, we call that the reference rectangle. And it allows us to place the asymptotes. So each of these branches will have an asymptote, and that asymptote will go through the center. Okay, and these two corner points. And the other asymptote will also go through the center and the other two corner points of that rectangle. Now, the thing to notice about those corner points, they are vertically aligned with the vertex on either side. So that's how we locate our corner points. So let's talk about standard form. It shouldn't surprise you too much that because we're talking about the difference in distances, instead of a plus, we have a minus. So the standard form for a hyperbola looks much like the standard form for an ellipse, with the difference, with the exception that we've replaced the plus sign with a minus sign. We're still centered at the point HK. My vertices are A units, left and right of my center point. So this is going to be at H minus A, K, and at H plus A. Okay. Now, my asymptotes are going to pass through a point. So these corner points are B units above and below the vertices. So for example, this point right here, that's going to be at the coordinates H minus A, comma, K plus B. And this corner point on the right, to upper right, is going to be at coordinates H plus A and K plus B. Think about that and make sure you can find these center point or these corner points. They're really kind of important because they're the only way that we determine the equations of the asymptotes to these curves. We can also have vertical hyperbolas, and vertical hyperbolas open up and down. The only difference is that the y term comes first. So we have y minus k squared over b squared minus x minus h squared over h squared. And these will always equal 1. Everything else is pretty much the same. We're still centered at the coordinates hk. We have vertices now, b units above and below. Let me close the door. Sorry about that. Okay. Notice it doesn't matter which is bigger. You can see from this graph that my horizontal distance, A, is actually bigger than B. That is irrelevant because what matters is which one is subtracted. So if X is subtracted from Y, then we have a vertical parabola or hyperbola. If Y is subtracted from X, we have a horizontal hyperbola. Notice that my distance C is defined as the square root of A squared plus B squared. And what that does is that distance C locates my foci from my center point. Okay? So let's graph this hyperbola. I've got a couple of Desmos graphs buried in here. So this Desmos graph just illustrates a horizontal hyperbola. You can see if I move my center point up, I can move my center point left and right. Okay, I can move my center point up and down by changing my K parameter. Now if I change A, remember A is the distance from the center to the focus, or center to the vertex. So I can squeeze it in tighter. And notice what's happening to my curves. That is because you see those corner points on our rectangle? Let me put in my reference rectangle. If those corner points move, that means my asymptotes move. And so when I change A, I change the slope of my asymptotes. And so the slope on my branches also changes now. V also affects this because I change the vertical component of the slope on the asymptotes. Okay. Those same things hold for a vertical hyperbola. The only difference is the thing opens up and down instead of left and right. All right. I encourage you, if you're struggling with these a little bit, to build yourself a Desmos graph and play with these parameters a little bit. So let's graph this guy. We're going to figure out what's going to happen, what's going to look like, what this thing's going to look like, and then we'll let Desmos do the drawing for us. So my hyperbola is given by x minus 2 squared over 4 minus y squared, which I'm actually going to write as y minus 0 squared over 25 equals 1. Now, y is subtracted from x, so we know that this is a horizontal hyperbola, right? We've got hk. We know that the center then is at the point 2, 0. We know that A equals 2 and B equals 5. So we know that my vertices are 2 units to the left and right of my center point. So sorry, I don't want to write that there. I'm going to write it over here. So my vertices are at 2 minus 2 is 0. The y-coordinate is unchanged. And 2 plus 2 is 4. And the y-coordinate is unchanged. Okay. We know that my corners of my reference rectangle are going to be at so let's take this one first, above and below this one. So 5, 0, and negative 5, 0. Nope, sorry, that's wrong. Above and below, the x-coordinate doesn't change. So 0, 5, and 0, negative 5, and at 4, 0, and 4, negative 5. All right, so let's put some information on my Desmos graph. Let's find my horizontal. Let's close that one, it's in my way. This is my horizontal. And what did I say? I said A was 2. We're going to turn off the hyperbola for a minute. We're going to turn off actually everything but my points. I said A was 2. I said B is 5. I said H is 2. And Y is 0. So K is 0. All right, so there is my reference rectangle. Now the next thing I'm going to put on are my asymptotes. And I've already had Desmos figure this out, but we're going to figure this out too. So here's the thing about my asymptotes. My asymptotes lie along the line that goes through the center and one corner point. So we'll say 0, 5. If you pay attention to this, you know that you can write, so k is a y coordinate, because this is hk, so y minus k is going to be equal to the slope. And your slope is always going to be, you're going to have one asymptote with slope b over a, and one asymptote with slope negative b over a. So for this particular hyperbola, your asymptotes are given by the equations y equals, okay, so y minus 0 is 0. 5 times x minus 2, because that's k. And 1 at y equals negative 5 times x minus 2. And we can double check that on our Desmos graph by putting those in. Y equals 5 times x minus 2. Whoops. I fibbed. Oh, that's because that should be 5 halves. There we go. A is 2, right? So my slope is 5 halves. There we go. Slope is b over a. Don't forget that bottom part, it's important. And the other one will be at negative 5 halves x minus 2. All right, so now we've got our reference rectangle. What do we have? Oh, okay, we've got the asymptotes, the vertices, the center. We need the transverse axis. The transverse axis, remember, is the one through which the vertices lie. In this case, that's going to be a horizontal line, so that means y equals, and y equals the y coordinate of the center, which is 0. And the conjugate axis is going to be a vertical line through the center, so x equals 2. Now, to graph this, you would graph your vertices, maybe a couple of other points, and then sketch your curve in along towards your asymptotes. The conjugates, or sorry, the foci, in order to find the foci, we need to find c. And c, remember, is the square root of a squared plus b squared. In this case, that's going to be the square root of 29, which is approximately equal to, well, 5.39. So I'm going to have foci at 2 minus the square root of 29, which is going to be negative 3.39, 0. And at 2 plus the square root of 29, so that's 7.39, 0. So let's go ahead and take a look at this graph. Here is my hyperbola. Let's put in the foci just so you can see where those live. That's going to be at 2 minus the square root of 29, 0, and 2 plus the square root of 29, 0. And there are our foci. Interestingly enough, if you're standing in any sort of a hyperbolic chamber, that focus point is going to act as an acoustic point, pretty much just exactly like the focus point for a parabola. Okay, so let's go back here and talk about how we're going to convert from expanded form to standard form. It should not surprise you too much that we're going to complete the square in order to do that. So we group all the variables together on one side, put the constant on the other side, complete the square on both variables as needed, and divide through by the constant term. And that's really all there is to it. So let's write 9y squared minus x squared equals minus negative 6x equals 10. So sorry about the line break there. That is 9y squared minus x squared minus 6x equals 10. Now, you recognize this as a hyperbola because both x and y are squared, but they have got, one has a positive coefficient and the other has a negative coefficient. So you know it is a hyperbola. So we're going to group the 9y squared because it's fine. It doesn't need to have anything done to it. We're going to group the x's together. Be careful with that minus sign. I'm going to leave it blank because I know I'm going to complete the square. I'm going to add half of 6 squared, so half of 6 is 3. Square that, we get 9. So I'm going to add negative 1 times 9. So I'm actually subtracting 9, so I'm subtracting 9 over here. So I get 9y squared minus x plus 3 squared equals 1. Divide through, oh, no, we're done. Equals 1, so we're done. Now this doesn't look right though. Think about what my constant, so I should have x minus k squared divided by b squared minus x minus h squared divided by a squared equals 1. What's b? Well, we can rewrite this as y squared divided by 1/9 minus x plus 3 squared divided by 1 equals 1. And then we can see that a squared equals 1, b squared equals 1/9. My center point is at -3, 0. And we could continue on from there. All right, let's do one last example because this one's kind of fun. So Jeff and Carl are out hunting Sasquatch. And Jeff is 10 miles west of Carl in an otherwise empty forest. At the stroke of midnight, Jeff records a Sasquatch call. Carl does too, but Carl records his Sasquatch call 9 seconds later. Sorry, yes, that is correct. Jeff hears the Sasquatch first. Now, Jeff and Carl know that the speed of sound that night is 760 miles per hour. So they're trying to determine a hyperbolic path determine the path along which the Sasquatch could be traveling. In other words, if they know If they can figure this out, then they can limit their search for tracks to this pathway. Because Sasquatch is somewhere on one of these two branches. Now, why a hyperbolic path? Well, we're going to use a hyperbolic path because this is exactly the situation for which a hyperbola is defined. We know Sasquatch is somewhere between Jeff and Carl. So the difference between his separation from Carl and his separation from Jeff is going to be some constant number that we can figure out. So here's how we figure this out. We know that the Sasquatch is closer to Jeff because Jeff, here's the Sasquatch first. And we can figure out how much closer the Sasquatch is using the fact that Jeff heard the Sasquatch 9 seconds earlier. So we figure that out. So what we're really doing is we're saying, all right, well, we know that Sasquatch is some distance d, and that is equal to the difference between the distance to Jeff and the distance to Carl. And we can figure this out because this distance is going to be equal to the difference in times where they heard the Sasquatch. So that's the speed of sound, which is 760 miles per hour, multiplied by the duration difference. So we got to go from hours to seconds and then multiply by the 9 seconds. And we get the Sasquatch was 1.9 miles closer to Jeff than to Carl. Okay. Carl and Jeff are located at the foci. Now it's convenient to introduce an axis system here, and because we are defining this system, we get to put the axes where we want them. So we're going to put Carl and Jeff on the x-axis, and we're going to put the y-axis halfway in between them. That's convenient because it puts my center, my HK, at the point 0, 0. Because Carl and Jeff are at the focus point, we know that C is 5 because each of them are 5 miles from the center. If you read the textbook, I haven't mentioned this yet in my lecture, but if you've read the textbook, you know that A is actually equal to D over 2. This is going to be an important thing that you probably want to memorize. So that means that if we've got D, we've got A. So A is 1.9 divided by 2, which is, in this case, 0.95. Remember that C equals the square root of A squared plus B squared. So we can find C. We know C, we know A. We can find B, which I messed up in my notes, so let's do this together. So 25 is going to equal the square root of 0.95 squared. Whoops, sorry, take out that square root of 0.95 squared plus B squared. No. No, I didn't mess this up in my notes. Okay, it just looked like I did. So that means that B squared is 24.0975. So here is the equation. So the reason why this matters is because they could take a map, right? Draw it to scale, scribe on their axis system. Given technology, You can probably figure out how to put that in decimals or overlay a decimals type graphing utility over the top of a map. Write down your equation, which is x squared divided by 0.95 squared, which is 0.9025 minus y squared over 24.0975 equals 1. Remember that Sasquatch is closer to Jeff, so Sasquatch was somewhere along this hyperbolic path. You could scribe this path onto your map and walk that same path searching for Sasquatch sign. You can't get a picture of Sasquatch because he's moved on, but you can find your tracks. Maybe, if you believe in Sasquatch. All right, let's wrap it up real quick. So, strategies for identifying conic sections. It's actually not too bad. They're pretty easy to identify if you know your standard forms. So that's a great big if. You have to memorize the standard forms of each of these curves. If only one variable is squared, you've got a parabola. If both variables are squared, look at the coefficients of x squared and y squared. We're going to call those A and B, capital A and capital B for this conversation. If those two coefficients are equal, you have a circle. If those two coefficients are unequal, but they both have the same sign, you have an ellipse. If those coefficients are unequal and have different signs, your equation will describe a hyperbola. Once you identify the shape, put the equation into the appropriate standard form, and bing, bang, boom, all this information will fall out in your lap. All right, folks, that is actually the last topic for this term. So, I've enjoyed making these recordings for you, and a second. And I've enjoyed working with you this term. If you have any questions between now and the final exam, please do get a hold of me or by email or phone, and we'll get together one way or another. I want to get those questions answered for you. Good luck on the final. Look at the course shell for additional announcements between now and then. And good luck in the remainder of your studies. Talk to you all. Well, I won't. You're done listening to me, so do good math.